Hello! In this video, we are going to prove the following theorem. There is a bijection from the power set of the positive integers to the real numbers. Now, to prove this, we are going to prove that there is an injective function from the power set of the positive integers to the real numbers, and then we're going to prove there is an injective function from the real numbers to the power set of the positive integers. Because then, by the Cantor-Schroeder-Bernstein theorem, that implies that there exists a bijection from the power set of the positive integers to the real numbers. So, we're first going to show there's an injection from the power set of the positive integers to the real numbers. And to do that, let's recall the following result, which we have proven. Let an comma bn from n equals 1 to infinity be a nested sequence of closed bounded intervals with the property that limit as n approaches infinity of bn minus an is equal to 0. Then the intersection of all of these closed intervals is a singleton set, right? It consists of exactly one real number. So in other words, there is exactly one real number which belongs to every single one of these closed bounded intervals. So to get an idea of what's happening here, we have our first closed interval, a1 comma b1. We have our second closed interval, a2 comma b2. It is contained in the previous interval. We have our next interval, a3 comma b3. Right? It's contained in the previous interval, and so on. Right? The fact that each interval is contained in the interval before it is what it means for the sequence to be nested. Right? So this is going to keep going on, right? But this sequence of closed intervals also has the property that the limit of the difference between the endpoints is going to converge to 0. So, turns out, when that happens, well, there's going to be exactly one real number which belongs to every single one of these closed bounded intervals. Right? That is what this is saying. Now, we can use this result to introduce the concept of decimal representations. So let dn from n equals 1 to infinity be a sequence, such that every term in the sequence is an integer between 0 and 9. We define 0.d1, d2, d3, ... to be the unique real number which belongs to this intersection of closed intervals. Now, this is just the notation we're using to represent the unique real number which belongs to this intersection of closed intervals. What we're doing here is we're mapping each sequence of this type to a real number, such that this is the only real number which belongs to this set. So, to show that this definition makes sense, we want to show that this set consists of exactly one real number. And to see how, well, if we consider this sequence of closed intervals from n equals 1 to infinity, well, we know is a sequence of closed bounded intervals. We want to show that it is a nested sequence, and also that the limit of the difference between the endpoints will converge to 0. Now, it's pretty clear that the limit of the difference between the endpoints is going to converge to 0, because if we take the difference between the two endpoints in any closed interval, then this is what we have. But that's precisely 1 over 10 to the n. So, the difference between the two endpoints in any closed interval that we have here will be equal to 1 over 10 to the n. So really, we're asking ourselves about the limit as n approaches infinity of 1 over 10 to the n, but that's clearly equal to 0, right? Because this is really just 1/10 to the power of n. And we have proven if b is any real number between 0 and 1, then the limit of the sequence b to the power of n is equal to 0, right? So this is just an instance of this result, right? So this tells us that the limit of the difference between the endpoints of the intervals will converge to 0. So we satisfy this condition. Now I want to verify that this sequence of closed bounded intervals is in fact nested. And to do that, we are going to show for every positive integer n, the nth interval contains the n plus 1th interval. So working with an arbitrary positive integer n, let's consider the left endpoint of the nth interval, which is this. Let's show that this is less than or equal to the left endpoint of the n plus 1th interval. Well, we know that this would have to be less than or equal to itself plus dn plus 1 over 10 to the n plus 1, right? Because we know that dn plus 1 is greater than or equal to 0. Therefore, dn plus 1 over 10 to the n plus 1 is greater than or equal to 0, right? Because this quantity is greater than or equal to 0, this inequality is true. But then, adding these two guys together, this is really just the sum from k equals 1 to n plus 1 of dk over 10 to the k. Right, and that is the left endpoint of the n plus 1th interval. We know that the left endpoint of the n plus 1th interval is less than the right endpoint of the n plus 1th interval. Right, in fact, that's going to be true for any interval because this is positive. But then, we want to show that the right endpoint of the n plus 1th interval is less than or equal to the right endpoint of the nth interval. Right, we want to show that this guy is less than or equal to this guy. And so to do that, let's take this sum and pull away the n plus 1th term. The next thing we're going to do is we're going to re-express 1 over 10 to the n plus 1 as 1 over 10 to the n minus 9 over 10 to the n plus 1. So we have this. But then, notice, these two terms right here is precisely the right endpoint of the nth interval. So what we're going to do is I'm going to group these two guys together and group these two guys together. And so the observation is dn plus 1 is an integer less than or equal to 9, right? dn plus 1 is less than or equal to 9. So then subtracting 9 on both sides, dn plus 1 minus 9 is less than or equal to 0. And if we divide a positive number like that, still less than or equal to 0, right? So this quantity that we have right here is less than or equal to 0. So because this quantity is less than or equal to 0, it follows that this entire thing must be less than or equal to this guy. And that's the right endpoint of the nth interval. Right, so what we see here now is we have the left endpoint of the nth interval is less than or equal to the left endpoint of the n plus 1th interval, which is less than the right endpoint of the n plus 1th interval, which is less than or equal to the right endpoint of the nth interval. That tells us that the nth interval contains the n plus 1th interval. So this is a nested sequence of closed bounded intervals, right? So we satisfy this condition as well. Because our sequence of closed bounded intervals is both nested and the limit of the difference of the endpoints converges to 0, well then according to this result, the intersection of these intervals contains exactly one real number. So it makes sense. We will define 0.d1, d2, d3, ... to be the unique real number in every single one of these closed bounded intervals. Now, one last thing I would like to note is that 0.d1, d2, d3, ... is actually a real number between 0 and 1, right? And you could prove that because 0.d1, d2, d3 belongs to every single one of these closed bounded intervals. So in particular, it belongs to the first one, right? So it belongs to this closed interval where we take n to be 1. So we have this. But actually, what's this sum? Well, we just substitute k for 1, so this is just d1 over 10. But we know that d1 is greater than or equal to 0. Therefore, d1 over 10 is greater than or equal to 0. Right, and as for the right-hand side, when we evaluate the sum, we just substitute k for 1. So that's just d1 over 10. Then we have plus 1 over 10. Now since d1 is between 0 and 9, we know d1 is less than or equal to 9. So this entire thing must be less than or equal to 9 over 10 plus 1 over 10. That's just equal to 1. So that's it. We see that this quantity lies between 0 and 1. So now we're going to get into proving this theorem. Now to start out the proof, for each subset of the positive integers, we are going to define a sequence corresponding to that subset. So for each subset of the positive integers a, we define the sequence dna from n equals 1 to infinity as follows. So if n is not an element of a, dna will be equal to 3, and if n is an element of a, then dna will be equal to 7. So this sequence is clearly a sequence such that every term in the sequence is an integer between 0 and 9. Right? In fact, it's always either 3 or 7. So because of that, we can consider the real number 0.d1a, d2a, d3a, and so on. Right? It is the unique real number which belongs to this set. Right? Instead of we would have dka here, dka here. So then, we use that idea. We're going to define a function from the power set of the positive integers to 0, 1 by doing that. We will prove that this function is injective. To do that, let's give ourselves two arbitrary subsets of positive integers. I'll call them s and t. And we were going to show if s is not equal to t, then f of s is not equal to f of t. So we'll suppose s is not equal to t. From here, we're going to show f of s is not equal to f of t. That will prove f is injective. So, what happens when s is not equal to t? Well, in that case, either s is not a subset of t, or t is not a subset of s, right? Now, if s is not a subset of t, then that means there is some element of s that is not an element of t. So s set minus t is non-empty. Now, on the other hand, if t is not a subset of s, then that means there's some element of t that is not an element of s. So t set minus s is non-empty. The idea is, if we consider the union of s set minus t and t set minus s, this is actually called the symmetric difference of s and t, right? If s set minus t is non-empty, then clearly the symmetric difference of s and t is non-empty. Similarly, if t set minus s is non-empty, then clearly the symmetric difference of s and t is non-empty, right? So what are we saying here? Well, if s is not equal to t, then one of these has to be true. But no matter which one is true, we see that the symmetric difference of s and t is non-empty. So it follows, symmetric difference of s and t is non-empty. And since the symmetric difference of S and T is non-empty, but also it's clearly a subset of the positive integers, because every element of the symmetric difference of S and T is going to be an element of S, or it's going to be an element of T, right? S and T are both subsets of the positive integers. So this is a subset of the positive integers. And since the symmetric difference of S and T is a subset of the positive integers, well, it's a non-empty subset of the positive integers. So it must have a smallest element by the well-ordering principle. And we're going to call the smallest element of the symmetric difference of S and T lambda. Now, I do want to talk about why we're doing this. So, first of all, what do f of s and f of t look like? F of s looks something like this, and f of t looks something like this. So, lambda tells us the first position where the corresponding decimal places are different. So for example, if lambda happens to be equal to 7, well then, this means that it is the first position where these two decimal places are different. So maybe this one's a 3 and this one's a 7, or this one's a 7 and this one's a 3, right? It's the first position where they're different. Everything before that, the corresponding decimal places are the same. The reason why is because anything smaller than lambda is not an element of the symmetric difference of S and T. And therefore, all positive integers smaller than lambda must be either an element of S and an element of T, or not an element of S and not an element of T. Now, if you're an element of S and you're an element of T, then according to how we've defined these sequences, the corresponding decimal places will be a 7. If you're not an element of S and not an element of T, then the corresponding decimal place is a 3, right? The corresponding decimal places are all equal when you're before lambda. But once you reach lambda, that's the first position where the decimal places are different. And so we're going to use that to show f of s is not equal to f of t. And so to do that, we're going to split this up into two cases. Either lambda is an element of s but not an element of t, or lambda is an element of t but not an element of s. We're first going to consider the case lambda is an element of s but not an element of t. If this happens, then according to how we defined these sequences, d lambda s will be equal to 7, d lambda t will be equal to 3. So this is 7, this is 3. We're going to end up showing that f of s is greater than f of t. So that's what we're going to show in this case. We're going to show f of s is greater than f of t. So what do we see? F of t, by definition, is 0.d1t, d2t, d3t, ... Now, we know, by definition, that this quantity belongs to every single one of these closed bounded intervals, where instead of dk, we're writing dkt. So, in particular, this quantity belongs to the lambdath interval, right? So this quantity belongs to this interval where we're replacing n with lambda. So that means this quantity must be less than or equal to this quantity where we replace n with lambda. We're replacing dk with dkt. Next, we're going to pull away the lambdath term of this sum. Well then, since lambda is not an element of t, according to the definition of the sequence, taking a to be t, what's d lambda t equal to? Well, lambda is not an element of t, so we have this case, therefore d lambda t is equal to 3. So we're going to replace d lambda t with 3. We can add the two fractions. adding these two together, we get 4 over 10 to the power of lambda. But actually, we should be able to take every term in this sum and replace the dkt with dks. Because the idea is, if we consider an arbitrary integer k between 1 and lambda minus 1, well then, k is a positive integer less than lambda. So k can't be an element of the symmetric difference of s and t, because lambda is the smallest element of the symmetric difference of s and t. So k is not an element of the symmetric difference of s and t. So now from here, we split it up into two cases. Either k is an element of s, or k is not an element of s. Case 1. If k is an element of s, then we must have that k is an element of t. Otherwise, if k is not an element of t, then k is an element of s set minus t, which means k is an element of the symmetric difference of s and t, which gives us a contradiction. So yeah, k must be an element of t. But now let's go to the definition of these sequences. Since k is an element of s, that means we fall under this case. dks is equal to 7. And similarly, because k is an element of t, we're going to have dkt equal to 7 as well. So they're both equal. So that completes case 1. Now let's move on to case 2. What happens if k is not an element of s? Well then, k must be not an element of t, right? Because what goes wrong if k is an element of t? If k is an element of t, then that means k must be an element of t set minus s, which means k is an element of the symmetric difference of s and t, which gives us a contradiction. So yeah, k is not an element of t. But then from here, we go to the definition of these sequences. Well, since k is not an element of s, we fall under the first case this time. So dks is equal to 3. And since k is not an element of t, we also get dkt equal to 3. So they're both equal once again. Since k could be any integer between 1 and lambda minus 1, that tells us that we could take each term of the sum, replace the dkt with dks. But now what we do here is, we note that 4 is less than 7. So this entire thing must be less than itself. We replace the 4 with 7, however. But actually, d lambda s is equal to 7, right? Because we see that lambda is an element of s. So according to the definition of these sequences, we fall under this case, right? D lambda s must be equal to 7. So we can replace the 7 with d lambda s. But then we can combine these two guys into a single sum, right? We get sum from k equals 1 to lambda of dks over 10 to the power of k. But now, what do we do from here? We consider the quantity 0.d1s, d2s, d3s, dot, dot, dot. We know that that quantity belongs to every single one of these closed bounded intervals, right? But we replace the dk with dks. So in particular, it belongs to the lambdath one. And therefore, 0.d1s, d2s, d3s, since it belongs to the lambdath closed interval that we have here, well, it must be greater than or equal to the left endpoint of the lambdath interval, which is precisely this. So that's what we get, but this is precisely f of s. So through this, through what we've established here, we see f of s greater than f of t. So that's what we get in case 1. That's what happens if lambda is an element of s and lambda is not an element of t. Now, if we consider the case, lambda is an element of t, but lambda is not an element of s, what happens? You get a similar argument as case 1. You will get f of t is greater than f of s. So no matter what, given any two elements of the power set of the positive integers, s and t, if s is not equal to t, then f of s is not going to be equal to f of t. So this tells us that f must be injective. So we have found an injective function from the power set of the positive integers to the closed interval 0, 1. In fact, we could treat f as though it's a function from the power set of the positive integers to the real numbers. So this also tells us that there exists an injective function from the power set of the positive integers to the real numbers. We really only need this to prove the result that we're going to be proving by the end of this video, but I want to take note of this because we're going to be using this to establish another quick corollary once we finish the proof of this result. So, we have shown that there exists an injective function from the power set of the positive integers to the real numbers. Now we're going to show there exists an injective function from the real numbers to the power set of the positive integers. Now, to show that there exists an injective function from the real numbers to the power set of the positive integers, we're first going to show that there exists an injective function from the real numbers to the power set of the rational numbers. And we define that function as follows. So we define a function g from the real numbers to the power set of the rational numbers by mapping each real number r to the set of rational numbers less than r. So to prove that this function is injective, let's give ourselves two arbitrary real numbers, r1 and r2, and we will suppose r1 is not equal to r2. From here, we're going to show that g of r1 is not equal to g of r2. To do that, we split this up into two cases. Either r1 is less than r2 or r2 is less than r1. Let's first consider the case r1 is less than r2. So, the idea is, between any two real numbers, there exists a rational number. So we can choose some rational number, say q0, which lies between r1 and r2. Well then, we see that q0 is a rational number such that q0 is less than r2, which means q0 belongs to the set of rational numbers less than r2, which means q0 belongs to g of r2. However, q0 does not belong to g of r1, because what goes wrong if q0 is an element of g of r1? Well, then that means q0 would have to be less than r1, contradicting the fact that q0 is greater than r1. So, since q0 is not an element of g of r1, but q0 is an element of g of r2, that means g of r1 can't be equal to g of r2, right? They don't have exactly the same elements. And so that's it. This completes case 1. In case 2, we have r2 less than r1, but we're going to get a really similar argument as case 1. We're also going to get g of r1 not equal to g of r2. And therefore, this tells us that g is injective. So we see that there exists an injective function from the real numbers to the power set of the rational numbers. So then from here, how can we obtain that there exists an injective function from the real numbers to the power set of the positive integers? Well, we have shown that there exists a bijection from the positive integers to the rational numbers. And since there's a bijection from the positive integers to the rational numbers, well then there must exist a bijection from the rational numbers to the positive integers, right? Just take the inverse of whatever bijection we have from positive integers to rational numbers. You have this. But then, it turns out, given any two sets A and B, if there is a bijection from A to B, that implies there is a bijection from the power set of A to the power set of B. Right? We have proven this in a previous video. We'll link it down in the description. So, using this property, this tells us that there exists a bijection from the power set of the rational numbers to the power set of the positive integers. But then, since we have an injection from the reals to the power set of the rationals, and we have an injection from the power set of the rationals to the power set of the positive integers, we know that a composition of injective functions is injective. So there must exist an injective function from the reals to the power set of the positive integers. And so at this point, we have shown there is an injection from this set to this set and an injection from this set to this set. So by the Cantor-Schroeder-Bernstein theorem, there's a bijection from the power set of the positive integers to R. And so this completes the proof. So remember, we have also shown there's an injective function from the power set of the positive integers to the closed interval 0, 1. But also clearly, there's an injective function from 0, 1 to the real numbers, right? Just take the identity function on the closed interval 0, 1. But also, let's remind ourselves, we've shown there is an injective function from the real numbers to the power set of the positive integers. So, from here, by composition of injective functions, we know that there's an injective function from the real numbers to the closed interval 0, 1. So, because there's an injective function from 0, 1 to the real numbers, and there's an injective function from the real numbers to 0, 1, by the Cantor-Schroeder-Bernstein theorem, there must be a bijection from the real numbers to the closed interval 0, 1. And so we get this as a corollary of it. So yeah. And so yeah, that's pretty much it for this video.